the previous video in this series, you learned how to import a printed circuit board from ODB++ format into ANSYS SI-Wave. You also saw how to examine the schematic to determine where to place the current sinks and voltage sources on the board. In this video, you'll continue to set up the power integrity analysis by assigning those current and voltage sources in SI-Wave. Our examination of the schematic and board is summarized in this table. It shows a list of the parts that need to have voltage and current sources assigned to them. As a next step, you'll assign these sources in SI-Wave. On the workflow wizard, click the Configure DCIR Drop Analysis button to bring up the DCIR configuration window. Select the power rails P1.0V through P3.3V. Now multi-select the reference designators U100, U201, and U800, which denote the microprocessor, RAM, and the FPGA. These all consume power, so from the Source Probe drop-down menu, select Current Source and click Update. Current sources for these selected designators are assigned. Modify the current for each of these reference designators as shown here. These current values come from the manufacturer's data sheets. So these are the current sink definitions. Next, define voltage sources. First, include the nets L3041, L5031, and XV-bus. These nets are on the output pins of the voltage regulators. Multi-select P703, U503, and U802. These denote the micro USB connector, multifunctional power management unit, and buck step-down regulator, respectively. Now simultaneously define voltage sources. If you miss any of the nets during multiple selection, you can always update them later as shown here. Change the default values of the voltages to reflect the actual voltages in this design. At this point, the current sink and voltage source definitions are complete. Next, click the Configure Simulation button. Since this is a clean design, you can skip validation. Click Simulate. Enter a meaningful simulation name. This name can help you keep track of the analysis variations that you run. Select the micro USB source and set its negative pin to be the ground reference. All voltages on the board will be displayed relative to it. Click Launch to start the simulation. The simulation completes in about 30 seconds. For post-processing, go to Results and select DCIR Drop and Currents Voltages from the shortcut menu. Select J to see the current density on the board. The current flow in the power distribution network is impacted by plane cutouts, vias, and other non-ideal features. Regions of high current density under the ICs are highlighted in red. These DC current plots help you to see what parts of the board may need to be redesigned to avoid excessive voltage drop or exceeding the current carrying limits of the vias. You can generate a power tree in SI-Wave. Click DCIR Drop from the Results tab. Select Export Power Tree. You can define limits for current and voltage and choose to include the objects of interest. In this case, accept the default and click OK to save the power tree graphic in the desired location. The power tree shows the current and voltage drop across each branch and each component in the power network. Actual values are compared with expected values to see whether they are within the tolerance. Under Results, click the DCIR Drop tab and select IcePack Power Map to see the thermal cells across different layers. SI-Wave computes the ohmic power loss dissipated in each of these cells and sends them to the thermal solver in IcePack. A recent improvement in the SI-Wave IcePack link is the ability to transfer the I²R power losses on a triangular mesh, allowing for smoother interpolation and smaller mesh sizes in IcePack. You can easily initiate IcePack thermal simulation from SI-Wave. On the Simulation tab, click IcePack. You can specify different types of thermal simulation. For this PCB, you can either set natural convection or forced convection as a thermal simulation type. First, select natural convection, still air. SI-Wave has computed the ohmic power loss in the metal traces and planes, but for a complete thermal analysis, IcePack also needs to know the power dissipated by the active devices. For the ICs and voltage regulators, enter power dissipation values. Obtain these values directly from the datasheets of these parts, or calculate them from the available information. For example, the data sheet for the step-down regulator U802 indicates a maximum recommended load current of 350 milliamps. If you're operating at the maximum current, with a 5-volt input and a 1.2 volt output, the power can be calculated by taking 5 volts minus 1.2 volts, and then multiplying that difference by 350 milliamps to get a power dissipation of 1.33 watts. The 1.33 watt power dissipation entered here for the buck regulator U802 is probably exaggerated, but this will help demonstrate what happens when a component is running too hot. Include heat sinks for these parts. Press Enter to launch the simulation. This runs the IcePack solver and calculates heat flow and temperatures across all objects included in the simulation. This concludes part 2 of this video series. In part 3, you'll perform post-processing by opening this project in IcePack.